Okay, I guess as the last people are coming in, let's get started. Welcome back to the afternoon session of the day. I have the great pleasure to introduce our first speaker, John Tsitsiklis, here from MIT, where he's at the Department of Electrical Engineering and Computer Science. John's really done a range of work in all of the disciplines, the fundamental areas that we've been discussing here: optimal control, stochastic systems, optimization, operations research, and I guess many of you know at least one of his books that he's written in these domains and have become the standard. So we're very happy that he agreed to give a talk where he's going to share his insights on reinforcement learning and the shades of reinforcement learning. Thank you.
All right, good afternoon. Thank you for being here. I would really like to thank the organizers first for organizing this amazing event. I think it is extremely timely for our community. And I also want to thank them for inviting me to speak here, although I only thank them with some ambivalence because I didn't seem I had the option of saying no, and now I'm stuck to talk about a field that I last touched 20 years ago. So the only thing I can do is to give a little bit of a subjective narrative about how I see or saw a few things, run you through the history. And to start on that, since it's going to be a narrative, I guess I had to get some inspiration from the literature, and that's where the title of the talk is coming in. Get some inspiration from there. All right, but also there is substance in that reinforcement learning does come in many different shades. It's a term that's a little bit ambiguous, so we are going to get into that. So I'm going to start kind of historically. We always start from stochastic control and Bellman and move downwards and talk about various dimensions of reinforcement learning and ways to think about it. So what's reinforcement learning? Well, really, reinforcement learning is mostly a methodology for dealing with stochastic control problems. And stochastic control is sort of an old field. It deals with systems that have a state. They have a controller that makes decisions or takes actions based on the state of the system. And here, it's with shame that I have to acknowledge this transition I've made this year. Instead of using X for the state, I'm becoming an AI person and writing S for a state. Okay. So you take that S, the controller does what it does, and then the system evolves according to certain dynamics, described either by equations or by transition kernels. And on top of that, there is a cost at each stage that describes how well we think we're doing at a particular state when we take a particular action. Okay, here I didn't do the AI transition to talk about rewards. I'm still an engineer. Engineers are supposed to avoid bad things, so they think of costs and bad case scenarios. I guess in the new world, people are after revenue and all that, so they tend to talk about maximizing rewards. Of course, mathematically, everything is equivalent. So we have this cost per stage, and we're interested in the cost that we're going to incur over a certain time horizon. And there's a discount factor. Typically, it's a number gamma that's less than 1, so that future costs get weighted less. So the object is to design a policy. That's the policy pi, is what the controller does. For any given policy, you have an expected cost, and that expected cost depends, of course, in the initial state S0. Let's see, is that? Okay, I got it. All right, and we want to minimize that over the space of all policies. And we call that the optimal cost that we get depends, of course, on the initial state, and we call it the optimal value function. All right, so the horizon of the problem, there's many variations of this. If you open a dynamic programming textbook, you'll see all those variations. Much of the work is done on this setting where we have a discount factor less than 1, and the horizon is infinite, so that one can look at policies that are stationary, do not depend on the specific time. On the other hand, something that is kind of forgotten is that often the discounted cost is a proxy for a real cost, which is an average cost. If we have a system that's going to be operating for a very, very long time and you want it to kind of be stable and do nice things, it's really the average cost that's important. But because mathematically average cost is a little more complicated, people kind of fall back into the discounted cost framework and say, let's take a discount factor close to 1, and that's roughly a good approximation of the average cost problem. All right, this is probably most of the math you're going to see in what I'm going to say. So the subject starts with Bellman, 1957. He comes up with a dynamic programming methodology, which is the methodology for calculating those value functions and for finding optimal controllers. For me, the classical period starts when I was a student. I read from cover to cover Dimitri's textbook on dynamic programming, and I was lucky to have that be the first course that I taught in my career. So I really love this subject. And what's the idea in dynamic programming? When you're contemplating an action, you think about the current cost that you're going to get, but you also contemplate what's going to be my next state and what's going to be the cost starting from my next state. And I want to choose an action that minimizes the sum of those two terms. That's Bellman's idea, and it leads to an equation that tells you that the optimal cost starting from a certain state is found as follows. You consider all possible actions you might take, you look at the immediate cost, and then you look at the expected cost starting from the next state, assuming that from the next state you're going to do the optimal thing, so your future cost to go is given by that same value function V star. And the discount factor goes there because future costs get discounted by a certain factor. And this is really a system of equations. You have one unknown V star of S for every state. You have as many equations as unknowns, and in principle, you can solve it. So in the old days, people would look into variations and extensions of this problem, infinite state spaces, infinite dimensional state spaces, whatever, and start writing down papers, paper after paper, about necessary and sufficient conditions for this equation to have existence and uniqueness, and perhaps occasionally write some theoretical algorithms that are algorithms on paper, but without necessarily worrying very much about whether these are real algorithms or not. Bellman from early on had the big insight that proving those theorems, yes, any competent mathematician can do it. On the other hand, to get good numerical solutions to those problems is not an easy affair. That's where the art comes in. Much more sophistication and ability is required to develop methods that actually work. And he also realized that these problems tend to become messy. They suffer from the curse of dimensionality. State spaces typically are large, too large to be handled by a computer, too large to view this system just as a system of equations and try to solve it. So what does one do for messy problems? One starts to approximate. The standard way, the first things that people did were based on the framework of numerical analysis, where you have a continuous state space, you discretize it, you sample it, the same way that one solves partial differential equations, for example. But even from the time of back then, Bellman also made the observation that a good way of approaching those problems would be, instead of having one value of V star, one value of the value function at each state, you might want to consider only value functions with a certain structure, parametrized. For example, let's say V star, I'm going to approximate it by a polynomial and try to fit polynomials to approximate the right V star. And this is, of course, an idea that's the basis of a lot that's happening these days. It's interesting to realize that it was in Bellman's mind, although at that time this idea did not really get pushed forward. All right, so let's fast forward a little bit. What's happening mid-80s and 90s when I sort of got involved into this field? Wait. Am I missing a slide? Okay. All right. So while dynamic programming and stochastic control were alive, there was a different stream of thinking in the AI field where people were saying, how can we get systems by themselves to act intelligently, interact with the environment like little babies do, and learn how to act? And these ideas, some of them were vague, some of them had more substance. They resulted in algorithms like Q-learning, temporal difference learning, and so on. And these were described in the first book with reinforcement learning in its title by Barto and Sutton that presented those methods and the sort of general framework coming with an AI narrative. For us in our field, Dimitri and I were lucky that some friends of ours pointed us to that literature and said that maybe it has something to do with stuff that you know. And one quickly realizes that what one has there is dynamic programming. You have iterations and updates based on perhaps noisy samples. So that means stochastic approximation methods of the Robbins-Monroe type. You're doing updates at different states as you visit them, so that means asynchronous algorithms. That's another topic that Dimitri had done seminal work for in the context of dynamic programming, and all that together with function approximation. So what do we have? It's really methods for doing approximate dynamic programming, and that was the point of view that we took when we wrote our book. We called it neurodynamic programming, the message being that it's basically dynamic programming, but you also use function approximation, for example, neural networks, but not necessarily neural networks. Now, the two books, in some sense, covered roughly the same types of topics, but okay, with different style. Barto and Sutton were a little more intuitive. We tended to be a little more math-heavy. But the framing is really different. One is about learning with interactions with the environment. In our mind, it was just what you do when you sit in your computer, you want to solve a dynamic programming problem. It's a big one. You'll approximate, you do whatever you can think of doing, and move forward. So even though the algorithms are the same, the mindset is quite different. What else was happening those days? There's an old traditional field called adaptive control, which deals with very much the same type of questions. You have a system, you don't know it necessarily that well, and as it operates, you want to adjust your controller so that they do the right thing. It's a field that has reached some maturity, but unfortunately, the methods of adaptive control are hard, complicated. You really need deep knowledge to make something work, and the scope is not necessarily as big as one might have wished. And partly as a reaction to that, the field of robust control also came into existence, where it's a different perspective. Instead of trying to adapt to possible changes in what my system is, let me just design a controller that's going to work no matter what my system is within a certain class of systems that I know. And that field has also picked up a lot of steam, and it's a centerpiece of control theory these days. So what happened then? After our book and a couple of PhD theses after that, I sort of left that field for two reasons. One of the reasons was that on the theoretical point of view, we felt that we got all the low-hanging fruit, and that the next generation of results one would wish to get, you would have to be able to say something nice about what the neural networks are doing in your loop. But general neural networks, there's very much that you can say. I guess these days people are trying to say as much as they can, but especially back in those days, there was nothing to say. Yeah, they have a universal approximation property, and that's where the story ended pretty much. So you couldn't really prove anything particularly poignant for the control setting. That was one issue. The other issue was you could have students do thesis on sort of practical type problems. Yeah, you do a case study. I beat the practitioners by 10%. So what? You cannot even get a faculty job interview if you were to do a thesis like that. So then just left the field, lied down. Who recognizes this guy? Okay, so that's Rip Van Winkle, who went to sleep was in the Catskills and went to sleep at some point before the American Revolution. So that's 1999 for me. And how long did he sleep? He slept for exactly 20 years. And that brings us to today. So So he wakes up, and what does he see in the world? Okay, I already answered that. So what does he see in the world? Many things have changed. X has become S. Okay. Okay. Now, there's another thing that changed, that he looks at his rifle and realizes that it has been rusted and asks why that's happening. I don't want to think of this as a metaphor of anything. I'd rather not think about this. But the other thing that he found out was that suddenly reinforcement learning, which was kind of forgotten in an esoteric field, is now the hottest thing on the earth. Not just hot, it's seductively hot. It's this idea that you have agents, they interact via their actions with a stateful environment, and miraculous things happen, and you open the New York Times, and you read about AlphaGo and AlphaZero, where systems learn how to interact and do amazing things. Well, they didn't exactly interact with the environment. They interacted with a humongous set of computers who were burning a few forests to learn how to play Go. But nevertheless, they did something that had that feeling. And closer to the practical world, another sort of big success, more real success, Google controls its data centers for cooling and has saved real significant money by using machine learning and with some reinforcement learning in there. And the way that they did it is by using lots of historical data that they had collected about their cooling centers. So this is all great, but at this point you realize that there's a little bit of disconnect between those two successes and what you read on Wikipedia about what reinforcement learning is. There isn't really any interaction with the environment in those successes. It's a computer offline cranking and computing. It's not an online real-time action. And so that's the first kind of shade of learning and reinforcement learning that I want to focus on. And it's really a big dichotomy, whether you're computing and learning and training offline using a model or a simulator, as in most of the publicized successes, or whether you're trying to do things in real time by interacting with the physical system. Some of the algorithms may be the same, but they're really different problems. In offline, during your training, you play the game, and whatever happens, your costs and rewards are with monopoly money. In online, you're dealing with real Swiss francs. You have to pay whatever happens. To put it differently, if you die in the offline training, you push the reset button and you do another episode. If your airplane crashes online, you're dead for real. So that makes the problems fundamentally different, and there should be different concerns in these two settings. Yeah, some of the algorithms look the same, but there are big differences in the background. Now, in the offline setting, it's not just a model simulator. You might have an actual robot that you're playing with, but there you will be a little more limited in data. You cannot do 1 billion episodes of robot training. Or you might have to work with historical data, as is common in some of the health and finance applications that people are trying. I would say that out of all those versions, maybe the very challenging one is this one, playing with historical data. It was mentioned yesterday about the issues of counterfactuals and all that. That's a big challenge dealing with historical data. Plus, when you have historical data dealing with patients, for example, who knows what hidden latent variables are there that have affected the treatments of the patients and that really confound you, and it's not clear how much you can learn to act based on historical data. So under some assumptions, you will be able to do some things, but one has to be extra careful there. Now, the dichotomy is not completely clear. Even if you are online, you can still use your model and simulator to do things. Anything that can be done offline, in principle, can also be done online if you have big enough computers. Or you may want to do things like in model predictive control or in look ahead. You use your model and simulator to look a few steps ahead of time. So that division, exactly offline, online, versus whether you have a model simulator or not, they're not entirely correlated. I think the big distinction between offline and online is what is really the cost that you're paying. Is it real with real consequences or not? And the two settings also mean that the complexity aspects of the problem that you need to focus on and try to do some theory are different. In the offline setting, you care about how much information do I need to get about my problem to be able to find an epsilon optimal solution. If you take a problem with continuous state spaces in d dimensions, elementary arguments, you'll see that you need 1 over epsilon to the d data points under some Lipschitz assumptions to do anything. And once you have so many data points, yeah, you can get epsilon approximate solutions. So information-based bounds show up there. Now, these bounds are worst case, where you have a worst possible Lipschitz function with a given Lipschitz constant. You will say that in practice, it's not arbitrary functions. They have some structure. Maybe they have succinct representations. And indeed, in most of the engineering problems that we deal with, they tend to have a smaller set of parameters. The problem can be succinctly described with a certain number of parameters, whereas the real state space is exponentially large in the number of parameters. So that's great from the information point of view, but at that point, the more standard computational complexity theory comes in, and it tells you, yes, you can get a description of your problem, but interesting problems will turn out to be computationally intractable. So some of these problems are provably exponential time. I'm not even talking NP hard. We're talking much higher than that. So they're exponential time, and that's a generic feature of these problems. And in some ways, that's also a bottleneck in how much you can hope to prove. These are real bottlenecks, and it's part of the depressing story, at least for theoreticians. Whereas in the online world, it's a different question. Is a more statistical one, and there's a big literature. Yes, Emma Stock yesterday mentioned some of the results. I haven't kept track of that literature. I just copied and pasted something from one of the papers. One will get estimates like this, that the number of samples that you need scales this way with the size of the state space. And the key point here is that this is linear in the state space. Great if you're dealing with something that has a structure like a multi-armed bandit problem, or where you're trying a few different advertisements. But for any system of the type that this community might be more interested in, that has interesting dynamics in it, the state space is already large. So whether you prove such a result and whether it's tight basically does not really have a bearing on what you would do. Okay, the real system will actually have some structure. You don't need to learn transition probabilities at each and every state. You need to exploit that structure, and then your sample complexity would be much lower. But then you are in the domain of succinct descriptions, and you start hitting the other barrier that has to do with the computational complexity even after you get the succinct description. So bottom line of all this discussion is that there's different types of issues that are more relevant to a theoretician, depending on whether you're looking at the offline or the online setting. Both are useful in different contexts, but one needs to always remember what context one has in mind. So the other shade that comes in, and I guess some people might enjoy debate about that, is what to do about models. There's this term model-free, which I think Andres yesterday actually did put it in quotes, and I'm following the same, because it's an ambiguous term. I think different people mean different things about it. The strange thing is that some people think that being model-free is a virtue, whereas I would consider it that it's a terrible situation to be in, that you would like to avoid and get around it. Now, without defining what model-free is, basically, if you have a model or a simulator, your choice is, do you use it to the largest extent possible, or do you pretend that it's not there and you just use it for a few oracle calls here and there? Well, obviously, you should use it as much as possible, so push all the way of using models. I think that discussion only gets interesting when you deal with physical or historical data, where you have the standard problem in data science and statistics, leaving control aside. When you have data, do you try to come up with a decision directly from the data, even a statistical decision, or do you try to first build a model and then optimize the model and come up with that decision? The answer will depend on the context, but there's nothing really special about the control context for this. It's a sort of basic statistic question that shows up in statistics more generally. All right. Have to really go fast. About practical research, I will just point out this statement by my colleague Alexander Madry that says that by having too many people work on benchmarks and report on benchmarks, we're not doing very well for understanding what the methods do, and that one needs to be a little more systematic when doing that. And finally, there's a bunch of problems that I could think about how to do theoretical research. And as I'm running out of time, I'll just show you that slide. And basically, what the type of research that I find more interesting is one that focuses on sanity checks that tell you that certain methods are fundamentally sound and some methods are fundamentally unsound. And what does it mean fundamentally sound? That if you make big, strong assumptions, that the method will still work well. And I have an example of a negative result and a positive result for value iteration and policy iteration. There are still open problems about the different types of problems here, and maybe some people here will pick them up or do the next PhD thesis on those. Okay, and I'll stop here, and thank you.
We have time for questions.
Well, I was to say a few things that when you also have dynamics there, the discussion changes from what you see in the typical machine learning type of literature, that stability is important, and that there's some research agendas there. I was very happy to see that a lot of that is actually happening. There are lots of great results that I heard even in this meeting. So these are probably not new things to most of the audience here.
Are there any questions that have come up in the meanwhile? Okay. Yes.
I guess speculating is always difficult, but if you were to sleep for another 20 years, what do you think, how do you think the landscape will change?
The hope would be that we would have understood what makes neural network magic to work, and will replace neural networks by something more tractable and structured, and that would also allow us to get better results in the reinforcement learning space. But I guess that's the wish list, I think, of many people who are thinking about this more deeply than I do. It's not clear if it's going to happen.
Good, I think that's a great remark to finish on. And let's thank John again for a wonderful talk.